Hi everyone. So we're going to do another video similar to the one that I did on curved mirrors. This time I'm going to be doing them on curved lenses, and hopefully this helps you guys understand a little bit about where the image is supposed to fall, what the signs of each parameter is. We're going to go through everything, so try to follow, and if you have any questions about this, just make sure to ask me. So in this case, we're going to draw everything from scratch. So remember always that we have to have, let me see if my pen works here. Oh, there we go. So we always have to have our principal axis. All right. And somewhere along this principal axis, I'm going to have my lens. And we're going to start with converging lenses. And there's a symbol for that, which you guys haven't learned yet. And that's the symbol for curved lenses that are biconvex. So these are converging lenses. It's biconvex, and yeah. All right. So we have F prime, C prime, F, and C. For some reason, my computer is a bit slow, so you're gonna maybe have to deal with a little bit of lag. I don't know what's going on here. All right, so we're going to start with the object being further away from C. So we're going to start with the object being here. And remember that this height of this object is right side up. Therefore, the height of the object is positive. And in this case, the focal length of the converging mirror is also positive. So I'm just going to write that down here. So I'm going to write that HO is positive, and that F is also positive. All right. So we have our three rules about how to draw the rays, and we're just going to use two of them as we did with the curved mirror. So the first one is parallel to the principal axis, and then through the focal point. Right, and the other one is through the focal points, but this time on this side of the axis, and then parallel. All right, and then therefore we can draw my object right there. What can we say about the object now? In the case of lenses, and the object being on the opposite side of the lens means that it's real. All right, so I mean, first of all, let me just say that DO is positive, and in this case DI is positive because it's a real image. The height of the object is negative because it's upside down, and it's smaller. So I'm going to say the magnification is between, how should I write this? The magnification, I won't write it, but the magnification is less than negative, it's between 0 and -1. So I can write that here, right? So it's greater than -1 and smaller than 0. All right? And the reason for that is it's upside down, that's what makes it negative. And it's smaller, so the magnification is less than, or the absolute value of the magnification is less than 1. All right? So that's the case when the object is placed at the object is placed further away than C. All right. So let's move on to a new page. Excuse me. We're going to do the same thing here. There's my lens. Remember again that I'm doing a convex or a biconvex lens, otherwise known as a converging lens. Okay. This time I'm going to put the object directly on C, and we'll see what happens. All right. Now, if you want to do a little prediction, we remember that when we had a converging mirror, when we had the object on C, the image also ended up on C, and the magnification was that it was equal, or it was the same size, just upside down. So let's see if we get the same thing here. I'm going to say that my focal point is positive. I'm going to say that my distance of my object is positive. And I'm going to say that the height of my object is upright, so it's also positive. So let's draw the ray diagram and see what happens. So we have parallel and through C. And then we have through F, sorry. And we have through F and then parallel. All right? And therefore, you can see here that the object is located directly on C. All right, similar to what we saw with the concave mirrors. So what can we say now about everything else? Is it upside down? Absolutely. So we can say that the height of the object, height of the image, sorry, is negative. It's the same size, so the magnification in this case is going to be exactly equal to -1. And it's negative because, again, it's upside down. What else can we say? Oh, and the distance of the image, since it's real, I can say that the distance of my image is positive. All right. Not so hard so far. Okay, let's move on to the object being between C and F, or C prime and F prime. All right. So same image as always. Okay, so there's that. We're ready to go. The height of the object is positive because it's right side up. The distance of the object is positive. And the focal length, because it's a converging mirror, is also positive. All right. So let's draw the rays. Always the same rules. And then through F. And then through F. And all the way there. All right. So we have a few things to note here. First of all, the image is located past C. On the other side of the lens. It is on the other side of the lens, so it's a real image, and therefore the distance of the image is positive. The height of the object is negative because it's upside down. And the magnification is actually smaller than -1. All right, because the object is bigger. Does everyone see that? Does everyone understand why it's smaller than -1? What I mean by smaller than -1 is like -2, -3, -4. And if I just remove the negative sign, it would be 2, 3, 4. It means it could be 2 times bigger, 3 times bigger, 4 times bigger. But there's a negative sign there because it designates that it's upside down. If you remember, the formula for magnification is HI over HO. So if HI is negative and HO is positive, then your magnification is going to be negative. All right? Let's do a few more. So there's my converging lens. There's F prime and C prime. There's F and C. This time my object, I'm just going to wait for my computer to catch up here. There you go. So here my object this time is going to be on F. Alright, and remember that this was also a special case when we dealt with curved mirrors, and we'll see if that's also a special case here. So here we go. What do we do? You can't do it, right? I'm just going to wait for my computer to catch up. I think I'm about to get a crash right here. There we go. All right. So it's never going to catch up. So in this case, there is no image at all. So there's no image when the distance of the object is equal to the distance of the object is equal to the focal point. I'm waiting for my computer to catch up. So I wrote D-I-O. I don't know how that came out like that, but it's actually supposed to say D-O. Let me just cross that out. It's supposed to say D-O. Like that. Okay? So when D-O is equal to F, there is no image. Okay, and then finally we're going to have the last situation. The computer is so slow. Okay, here we go. This time we're going to have the object in between F and the lens. Again, just going to wait for my computer to catch up. Wow, this is unbearably slow. There we go. Okay, so let's follow the ray diagrams and see what we get, and so that I can turn off this video and restart my computer because I think it's about to explode. So first parallel and through the focal point, and then through the focal point, and then whenever it hits the lens, which is back here actually, we have to go through the focal point. And so where do these two rays intersect? Well, it's not easy, but if I did this backwards drawing here, so I'm just going to change colors. So if I went there, and then parallel, and I move this one backwards, there's an intersection point right there. And therefore my image is right there. Okay? Wow, that's a big difference. But not surprising considering that we expected kind of something weird for this one, as similar that we saw to the converging mirror. So let's just draw what everything is. So the distance of the object is positive. Now the distance of the image in this case is now going to be negative because it's a virtual image, and therefore is located on the same side of the lens as the object. The height of the object is positive. The height of the image is positive, and the magnification is greater than 1. It's bigger and is right side up. All right? And as always, the focal point in this case is going to be positive because it's a converging mirror. So that's everything we need to know about converging lenses. All the signs are there. Everything is there. I'm going to start another video to doing diverging lenses, and hopefully my computer works a little bit faster, And we'll see that there is some very similarities, a lot of similarities with a diverging mirror. And that won't be surprising to you because we just did all of converging mirrors and converging lenses, and everything was pretty much the same thing. All right. So far, all we have to do is apply what we know about converging mirrors to converging lenses. All right. And we'll see how diverging lenses work in the next video. All right. Well, thank you. I hope that helped. If you have any questions, please let me know.